classification is very, very important. That is very useful in many applications, particularly in cybersecurity. Any security or any fraud detection, even in financial sector. By looking at the previous examples, we may be able to see the possibility of the current example. Okay, so this is something that we look at, we analyze the given data sets, and then we make ourselves ready to make decision. The previously well-known data, therefore, should have a label, which means if we have two types of data, good data or bad data, then there are some examples, some data instances should be labeled good, some others bad, things like that. If that is a financial data sets, then some data instances, you can say that is innocent data, or that is reliable data. Some other data may be fraud. Okay, this type of data may be fraud. That type of things that we need to set up. So training data sets, by the way, is important. Once we have a training data sets, of course, training data sets is collected from the real world application. Anyway, it is from the real world that represents the real world. If a real world said that is fraud, or that is attackable, okay, that is intrusion, then it is so, right? It is not by something like definitions, but it is by the real world examples. It can be applied to financial sector, cybersecurity. It can be applied to even medical sectors, right? The primary doctor may say, by listening to the symptoms that you describe about yourself, then your primary doctor may say, hey, I want to send you to some specialist. So how come he make that decision? Or how his decision is really accurate? May or may not be accurate, right? It may be accurate if it is if he has enough data sets, enough historics data sets, historical heuristics. Okay. So the first thing that we need to do, we learned this last week, right? We will do two things. Decision tree. So we need to construct a decision tree. And use of a decision tree is very, very simple. We just follow and trace the tree structures. That is very, very simple. The key issue in decision tree is how to construct. That is the key issue. So we will do that. That's the first issue, first hands-on that we are going to do today. The other hands-on is K nearest neighbor classifications. If we say, hey, I want to classify the given data with 30 neighbors, 30 closest neighbors, or 40, or 2,500, or whatever number that we want to classify. That's k nearest algorithms. That's what we want to use. We're not actually to develop the algorithm, but we're going to use it. There are actually two kinds of the tools available. One that'll be R, okay, and the other one is Python modules. There's a scientific kits available, so-called the scikit. So we can use that. But today we will look at R only for classification. Maybe today we will do R. Next week we will go back to Stanford textbook for clustering. And the week after that, then that is the last week of April. There I'm going to, for clustering, we can still use R or Python, probably Python. Let's try to do Python, okay? If you know how to use R for classification, then there is also clustering, okay? Ready? All right, as I said, I am not going to use RStudio, but I am going to use RScript. So we need to create a file, okay, and then run that file. Before doing, so what you need to do is for Windows users, this is it's still same thing in Mac users case. So bring up command terminal, command line terminals. Since I have already some of the data here, so I am going to relocate to that place by using change directory, and then I copied that path expression. That is a path expression, and hit enter. Then my current this current directory is there, where there I have all data, so many all data, and I have also. Oh, by the way, what I am going to use the data sets. I think this is the first time, right? This semester. Rather than a plain text file, I am going to use CSV files. Okay, so today we will use CSV files running in R script. And for clustering, hopefully we can do other data sets, maybe plain, or maybe CSV files. The CSV files is very, very common, and we can still use that. So bring the data from the CSV files in that machine learning tool in Python to cluster. That's what we are going to do. Okay. So, and also make sure that our script runs. Okay, it should be in your path expression. So that's, if you have this, then it means it runs, right? So you can see also version. What is the version? version of that is 4.0, 4.0.3. It's relatively recent, right? I'm not sure this is really the most recent ones, but it's not bad. And then I have all data. That's what I am going to work on. So one of the decision tree that I am going to construct is decision tree classical iris. Iris data is very common data. Okay, do I have iris data here? Yeah, I have iris data here. For example, if I can show this, maybe, yeah. As an example, okay? But this iris data, some of you may not know at all so far. So we're going to use something that we know, okay? So if you see here, iris data, then data sets is about 150, not many. And then this is some of the flowers, right? Sepal length, length of a sepal, width of a sepal, and length of petal, and then width of, and then species. Finally, if we have this kind of measurement, then we can say that is a setosa. Similarly, this is a label, right? If the iris flowers has this type of measurement, then that is versicolor, and the other one is virginica, and three kinds of decisions. Okay, this is labels. So if you want to construct the decisions tree, then you can simply say script decision tree decision t classifica iris dot r. The file looks like this. This is an R file. Okay. In order to do this, you need to first install the package, party packages. Okay, this is a partition, party for partition classification. You need to install it. Once installed, and then when you run, then every time you have to import, that is a library. I am going to use this library. Okay, and then read the CSV files from, I downloaded it, so I read it. And some of the data here is not numerical. Which one's not numerical? There's a species, the label, last item, that is not numerical. Non-numerical, then we need to factor it, okay? And then this is the function that we are using, okay? C3. I am going to, what this function can do, this function has the arguments, okay? So first arguments is, I am going to use, what is the label? Okay, I'm going to use the decision tree. What is the label? My label is a species. So the idea here is that if I have this kind of a number, okay, or that kind of number, then that decision tree tells us, hey, that is a setosa, okay? That's a decision. If a customer is described over this kind of number, then I can say, oh, that person is uh, maybe uh, disqualified for loan application. Or if we use this for the Homeland Security database for port authorities, TSA, um, the immigration decisions uh, at the airport, then based upon the data that they have, that they need to make a decisions whether they uh, permit them to enter into the country or denied. So send them back to where they are from, things like that. So that is the first argument is the label. I wanna make decisions for species based on what? Based on these kind of uh, data. Here we have plus signs, right? This is one attribute. This is another attribute, and another, and another. 4 attributes, which means I have 4 attributes, right? There's 2 attributes for sepal and 2 attributes for petals. And then what is your data? My data is iris. What is iris? Iris is red. Read the CSV, and then that's assigned to iris. So iris is my data. Okay. So this guy constructs the data. If you want to see the tree, then you can see this. The tree is automatically constructed. Okay, let's try see how it works. I want to hit enter for that. Okay, so that is done. And this is just constructed 751. This is a plot, R plot. This is a plot automatically plotted by executing that R files. So if I open it, then you may be able to see clearly there are decision trees. Okay, this is a decision trees. So what happens here is that which one that I want to see first? I want to see petal length, and if it is less than 1.9, then remember that how many data sets that we have? We have 150 data sets. At the first comparison, 1/3, 50 of them are already 100, which means I have 3 labels. So in this case, setosa. As far as petal length is less than 1.9, then that is likely setosa. Okay, so petal length, third element, if it is less than 1.9, so let's say here, this is less than 1.9, therefore that is a setosa, right? That is not 100% accurate, but it is likely. Let's see what happens to the other. Is there anything? This is setosa. I think luckily, all of them are, yeah, all 50 of them are setosa. Okay. If you see the others, leaf node here, y equals, there's a 3's, right? There are none of those setosa. 46, the 50 all setosa, and then 100 it can be split into two by looking at petal width of petals, and then 46 of them can be here. So 97% of those 46 will be the last label, which is Virginica. Okay, and then only 2% will be versicolor. And if that is the other case, then we still need to look at petal length again. And if it is less than 48, 4.8, then that is most likely the second one, okay, versicolor. And then 8 of them are 50-50, 0.5 and 0.5, which means if petal length is greater than 4.8, then it could be versicolor or Virginica. Okay, if it is a 4.8, if number is very high, if there is a very high number, for example 6.6, then there's a Virginica, and then 6.6, maybe 5.1, that is versicolor. Okay, if it is very high, that type of things can be constructed. What we will do here, we will practice small ones, okay, rather than something like this. So as an example, data is already here. Let's say this is the same example that we have in the slide, but I changed it a little bit to all the numbers, okay? But we can do that in this is original ones. Income is high, medium. This is not real number. Students, yes, no, and credit rating, fair, excellent, and most of them are the character, okay, not numerical. So I change it to numerical, first attempt. So without having to factor, without having to change it, without having to convert it. The idea here is that, let's say this is all the trading data sets. Then are they likely to buy a PC or not? In this buy computers, if there is a 0, then not buy. 1 means they will buy. They actually buy. They bought. This guy didn't buy. This guy bought. Things like that. This is some of the conditions in numerical ways. So we need to first determine what we will do. Okay. So I think we need to make a notepad, and then example pc.r. Okay. So, do you want to create a new file? Yes. All right. So we don't have to install, but we need to use a library. Library will be party, And then I would say the data that we need to read the CSV files from this location. This is the location, okay? So inside here, and then better to have a double backslash. I explained this why double backslash. If it is a forward, then that is okay. But only in data is this data file. So that is can by PC binary file and then CSV. And another is, let's say this guy has a header. So we can say header equal true. There is a header, and separate is, of course, that is a CSV file. So comma is the separator. So once this read, then we need to hold the data. So we can say that is can by PC, and I assigned it there. Okay, that's some assignment. So I call that the function. This is a function from this party. Then it can be read. Okay, and then because this is a string management, I need to say by PC all in string. No, we don't need to, but that's okay. And then C tree, run the C tree. The C tree, I want to construct a decision tree for what? For whether they buy computer or not. Buy computer, and then tilde followed by based on what? Based on student, income, credit rating, and then data is from by PC. And then plot. Well, I want to say I want to convert this to, I want to assign this to PC tree, and then plot PC tree. I always simply like this. And then let's see if I can save this as all files, and this should be all files, right? Let's see, what is my exam? This is not where we are. Type of classification all. So example PC here. Oh, this is all. Oh, luckily, that's fine. So make sure that is in all files. Okay, this is already just, you want to replace it, may or may not. Okay, and then see if works. Okay, so example pc.all, and come back here to see if we have new plots. Not yet, right? So one of the things that we need to do is that here, plot PC tree. Okay, save this. And again, see what happens. Oh, now it is a carry on top. Also, we have kind of this examples, right? So how many that we have right now? We have about 59 data sets, 60 including header, so 59. So 29 goes here and 29 goes there. So this kind of classification, this is not well classified. It doesn't mean much, right? But anyway, this is the case. So I want to do real examples. Don't save. So now you know how you can create construct, right? It doesn't mean much. Well, let's see, because I already had, let's say mortgage loan. This is a mortgage loan. That I already had. And this guy will play with the mortgage loan CSV files. So I am going to use that mortgage loan CSV, mortgage loan here. So what happens here is, let's say this guy has a paycheck, one. This guy has 1.5 paycheck, which means his own paycheck, and then yeah, another half-time paycheck. This guy is part-time paycheck. That's what this means. And bank balance, this guy has 111,000. A lot of bank because they want to buy. This is, I assume they want to buy a home, right? And then credit scores 720, 650, things like that. They're all relatively good, right? And then overdue. Is there any overdues? Payment overdues. This guy has no. This guy has yes. Okay. And then according to the uh, the bank home loan officer's record, with this I can say approve. With that approve. In this case denial. And then how many data sets that I have? I have 72 data sets from 1 to 70, 2 to 73, right? 2 to 73. So total 72. And then this guy is a test data sets. So up to this points in the same CSV files, up to that point, I have that is real data. Okay, that is a real decision trees. Decision that's made. And then whatever after this, there's no labels. So we need to put the labels here. Okay. This is very realistic, right? And my R file is this. Party, same thing. And then I read. And I want to split these files into two parts. One for training data sets. So it will will be used to build decision trees. The other, if there is no labels, that I am not going to include to use that labels to decision trees. So this is a can-learn data. From that can-learn, I want to make subsets. If that satisfies in the approval field, if it is not nil, okay. If it is available, NA means not available. If it is not available, then I want to make this can learn. And also, this column is not numerical, so I want to make this two columns, right? Overdue and then approval rates. Approval and overdue. Those two are not um, um, numerical data. Therefore, we need to say, hey, we need to uh, convert that to enumerated data. That function is called the factor. So we need to do that. And then we simply run that C-tree functions. We want to build a decision tree for approval columns based upon the rest of the columns. The data is can ln. This is something other than something that already decided. Okay, and then we plot that. So let's see what happens. So doggy is barking a lot. So mortgage loan all, that's this file, right? Okay, that's this file, mortgage loan. And I am going to okay. This is just sample, okay? The first six data sets are given. First six data sets. Okay, those data sets are repeated here. Doesn't mean much. And then this is done. So what happens here when you come back to that plot, I want to make sure that this is just constructed very nicely constructed. So first thing this guy consider is overdue. Okay, if there is no yes overdue, okay, then this is funny, no and yes together. Okay, yes, then it could be, we can also think of bank balance. If a bank balance is greater than 35,000, then we will have 12 records. Those 12 records will be yes, no. How come we have three values? We have only yes, no. Maybe something else. Probably the character was not. Is there some other? Yes, no, yes. this. There's a little bit or three cases. Let's say this is the third ones. It's not really the case. Maybe. Oh, it is because yeah. Oops. Let's say let's let's try to see.
Professor, is it because
And
you have a lowercase y?
which one?
A lowercase y?
Is there a lowercase y?
Yeah. Number line 34. I wonder maybe there's some like lower cases and that are throwing off the
Oh yeah. So that is something like this. Yeah, because of the data is not really. Yeah, that is true. But anyway, because this is a factors data, right? It should be accurate. That may be the reason. Oh, here is a no and a small yes, right? That may be the case. But this is automatically construct. Okay, um, and that well represents the real world data. Uh, in many cases, if we train some of the data, then the problem is that the training data. If we have a well trained data, then what happens here is that uh, according to that tree structures, there is no mistake at all because we just follow the tree structures, right? If it is well trained, then then uh, then there's an overfitting issue, which means uh, because it is well trained, it is well uh, it fits really well. Therefore, if there is uh, some erroneous situation occurs, then this guy cannot do anything. Only if we have a training data sets that represent the real world completely well, therefore that is overfitting, then it works only for that. That is the sometimes that is the issue. But other than that, decision tree is perfectly fine. Okay, so in all, the way that we can construct a decision is using this. Simply we read it and use the C-tree functions. Read.csv function to read, and then use the C-tree function to construct. And meanwhile, if there is some non-numeric data, then we need to factor them case by, I mean, the attribute by attribute. If you have many attributes, then you need to do all of those. Okay. So next issue is a k-nearest algorithm. That's what I am going to do. Okay. So um, I'm going to give you again the example of a k-nearest algorithm. That is that's what we are going to do is for example, I'm going to use the same example, same same CSV files. Okay, that is this, right? Using the same example. And then k-nearest algorithm is not really. If you see the textbook, the implementation textbook, I am going to use the same ones. On page 106, the one that I did was the page 104 and 105. 104 and 105. There is an example and exercise. In the example 4.12, then that it constructs the decision tree very nicely, right? That decision tree is not the same as that we generated. It depends on the training data sets, right? In this case, we have 3 layers. And then initially using the overdue and then bank balance and then credits. So how many leaf nodes that we have here? 1, 2, 3, 4, 5. 5 leaf nodes. This guy is again very similar to the others, right? And then based upon that examples, there is an exercise. What exercise asks you to do is to tweak the data a little bit. And then we see the decision tree will be completely different. Okay. If you see those 2 pages, page 105 and 104, each page there is a decision tree for the almost the same data sets, but it constructs the decision tree differently. So what happens here is that depending upon the training sets, your decision tree will be sometimes completely different. That's what this text tries to demonstrate. So collecting this training data sets is very, very important. Okay. And the next page, 106, we're going to use the KNN, K nearest neighbor algorithm to be used to classify. That's what we are going to do. Okay. So in this case, it is already alpha already defined, so I am going to post here. Okay, so it'll be like this. Okay. We need to import class. Okay. Library class. Remember the previously when we construct a decision tree, then we need to import the party, in this case class, and then read the same CSV files. Okay. And the columns that we are considering is these 3 columns. Approve is a label. That's what we want to label it. That's what we want to classify. So except this approve, the columns that we want to consider, then we list them. Okay, we concatenate that, which means that is a list. We list them, And then from this data, that data, I want to consider only paycheck, bank balance, and credits. That's what this guy can do. Okay, so data, this is just a variable. Dot doesn't mean much here. Altogether is this just string. Okay, let's say data that subset holds the data only up to this and up to right now up to this. Okay, but I want to eliminate the rest again here. So how we can eliminate that? And I assigned 1 colon 72 to test. This is a variable, simply variable. Variable represents 1 colon 72. So out of this data dot subset, I want to extract only this rows from the row number 1 to row number 72. Only 72 rows. That is called training data. And other than that, there's a minus test, then there's the test data. So test data will be only here, the last one, two, three, last five rows for test data, all above, that is the training data sets. So we have train D and test D. And approve, we still say that is character data sets, so we factor it. So we say that is the data. This again variable data dollar approve. Okay, and then finally we need to define what is the classification. What is the class label? So we can say train dot class label CL is approve data $ approve means data is this entire table. From that data, dollar followed by the attribute name. Okay, so dollar in this entire data, attribute is approve. So this is approve. This means data dollar approve. There, I want to select only first 72 rows, as I said here, first 72 rows. Okay, first 72 rows, which means up to this. That is my label to train. So I set everything, training data sets, test data sets, and then the labels. After that, we see KNN. KNN is a function. This function takes multiple arguments. Train equal train D. This is a resolved word. Train equal train D. Okay. Because we have a train equal or test equal, CL equal, K equal, probe equal, you don't need to put their arguments in this order because they already have a variable and value pairs. Okay, this is a variable that this KNN looks for, and then this is a value. So what is the training data sets? I can say train D. What is a test data sets? I can say test D. What is a class label? I would say train.cl. That's what we defined here, right? How many nearest neighbor that you want to consider? You want to consider 23, or we can increase this, see how it affects. And then we want to prove it. And then print K2. It returns so many things that we want to print it. K2. Okay, see how it works. Our script Okay, so that is that file, this file, and I want to run it. This guy returns whatever this whatever we print here, that is this. We have only one print statement, right? What this knn function returns, that is printed. See what is printed. So we have this guy is printed. Okay, we probe. The first element to know, second, third, fourth, fifth. Remember that we want to test 5, the last 5. I want to class this last 5. What these ones fall into, what this each rows falls into what categories? Is it yes or no? Okay, this is the decisions for about the loan applications. So this guy says the first one in the test there is a no, the rest yes. Okay, so this guy is only no, all others yes. Okay, so what happens here is that we can consider just right above. Compared to 73 and 74. Okay, both has one bank accounts, and they have very similar bank balance, and then credits are similar also. Only difference here, this guy has overdue, this guy has no overdues, but still denials. Okay, all of, if we consider all other examples. So what if we do, for example, we increase this to 150,000, okay, 150,000, and save this, and run the same example, but we change it only this elements. First row in the test data sets. See if that is still no, or if it is yes. So run it. In this case, they are all yes. We can try some others also. Let's say this guy is really good, right? But I want to change it to only 9,000 bank balance, no checks. Only I change this, okay? Bank balance. And see what happens. I'm curious. Oh, in the case, denial, right? Third one is denial. 1, 2, 3. Third one is denial. Based upon others. That makes sense, right? So KNN, K nearest neighbor algorithm works well, as you can see here. What if I change the code? Rather than 23, I want to do maybe 13, okay? Rather than 23. 23 nearest neighborhood algorithm, or 13 nearest neighborhood algorithm. See how it affects. Oh, one more denials. Okay, if we change that. Third and fourth, this guy also denials. Only that affects. This guy has a higher bank balance. Even if that is a low credits, all others similar, right? But because of this denial, that's what happens. Only I change this 13. If I change this even lower, say 9, see what happens. Still, they are okay. What if I do 33? that. 43. Still that is okay. What if I have 5? So there's 2 nodes. If we, this is a little, this is a like a possibility, some of the probabilities, right? So I'm sure the third one is no. Kind of 75, sure, no. Uh, but uh, this is a little different, right? This is, yeah, some of, I'm not sure what it is, but third one, surely no. All others, uh, not quite. That's what this KNN gives us. Let's see how that KNN interprets. And we look at that and then we will KNN. KNN requires returns. Functions collaboration. So this is a KNN functions to be used. Train equal, test equal, CL equal, A equal. Let's see how we can interpret. That's what I want to see. Interpret. Complete guide. What is KNN algorithm? Feature of the KNN, how KNN algorithm works. KNN algorithms with those implementations. KNN optimizations, comments.